trick with that and it arrested it up completely.
Well, that could happen, yeah. Not impossible.
Alright, today is a big day because we're going to leap into the third dimension and actually do the three-dimensional quantum mechanics instead of this would-be one-dimensional stuff, or one-dimensional QM is the way that would be. But we're going to make the leap into the third dimension. We'll say 11 dimensions for grad school, 10 dimensions or whatever. So, quantum mechanics, QM, in 3 dimensions.
What are we doing the fundamental postulates of quantum mechanics earlier?
Yeah, did we finish those up? I thought we did. I mean, we were, but I thought we finished those up. Yeah, I'm pretty sure we did. Oh, true enough. What? You're looking at your homework. No, we finished those. We're done with those. So it is in fact time to jump into the third dimension. So, yes.
We'll have a homework set next week.
Next week, yeah, not this week, because of the exam.
Can we make a deal?
What?
Can a homework next week due after Thanksgiving?
I'll think about it. I'll think about it. Don't talk to me next time. I'm not thinking about that right now. I'm not thinking about that right now. So, in 3 dimensions, we need position and momentum operators for every direction, basically. So we're going to have not just an X operator, but also a Y operator and a Z operator. Not just a momentum operator, but a momentum operator for the X direction, a momentum operator for the Y direction, a momentum operator for the Z direction. These operators are postulated to satisfy the canonical commutation relations that the X, Y, and Z operators commute with one another. So we're going to use X1 by definition is the X operator, X2 by definition is the Y operator, X sub 3 by definition is the Z operator. So Xi, Xj commutator is 0. The position operators commute with one another. Furthermore, we'll use subscripts on the momentum operator. So P1, P2, and P3 are Px, Py, and Pz. The momentum operators commute with one another. So Pi commutator with Pj is equal to 0. So in other words, it's possible to know where a particle is in principle. You could know all 3 components of its position, or you could know all 3 components of its momentum, but the x's and the p's satisfy the commutation relation that the commutator of xi with pj is I h bar Kronecker ij. Or in other words, that the x's and p's commute with one another unless it's the same direction we're talking about. So x does not commute with piece of x, but it does commute with piece of y and piece of z. And similarly for the other 2 position operators. And if we write down what they ought to be in the position basis, then those commutation relations are pretty obvious. becomes multiplied by x. The y operator simply becomes, multiplied by y. And of course, the z operator simply becomes multiplied by the variable z. This is all in the position basis. Whereas the operator p sub x is equal to minus I h bar partial with respect to x. P sub y, I'll put arrows to say it's represented by as opposed to literally equals, because we're in one particular basis, the position basis. P sub y should be minus I h bar partial with respect to y. And the momentum z component operator is minus I h bar partial with respect to z. With those representations, the commutation relations become pretty obvious because, for example, if I want to look at what's the commutator of x with p sub y, well, that goes into, we're looking for the commutator of x with minus I h bar d dy, and if I apply that to some test function, f of x, y, z, then really we're just talking about how, how the partial derivative with respect to y doesn't care about x. X to it is just a constant, so this would be equal to minus I h bar x df dy minus I h bar times d dy of x f, but d dy of xf is just x df dy. I'm guessing that you are looking for the keys to my heart.
Yes, sir.
Why, come and get them, my dear.
Oh, this is
Yeah, I know, this is like right after lunch, or maybe it's like that.
Thank you.
So you'll get 0 to the terms, will just cancel one out because of that. And similarly, if I do px commute with py, well, in one direction I'm going to get the partial with respect to x of the partial with respect to y. In the other direction I'm going to get the partial with respect to y of the partial with respect to x. And remember, partial derivatives don't care what order you take them. The second partial with respect to x and y of a function is equal to the second partial with respect to y and then x. So they don't care. So the p operators commute with one another in this representation, and any p commutes with any x as long as they're not the same direction that we're talking about. If we're talking about the same direction, if this was d dx of xf, well, that's when it matters, because then you would have two terms, because you'd have to differentiate x and f separately from one another. So these are the generic commutation relations which are realized by this particular representation in the x basis. In the position basis. Similarly, there's a momentum basis where we generalize what we saw in one dimension, namely, in the momentum basis, the p operators become multiplied by px, py, and pz, p sub x, p sub y, p sub z. And the position operators become plus ih bar dd px is the x operator, plus ih bar dd py is the y operator, plus ih bar dd pz is the z operator. And you can plug those in and get exactly the same commutation relations from that representation. Okay? Any questions? So essentially, we've just made kind of the natural leap that you would make to go up into the third dimension, or the second as well. We could stop at 2. Why, we could even go to 4 dimensions, but we're not, because as far as we know, space doesn't have 4 dimensions. And even if it does, it's little curl up things and all that will be different with those. So, all right. Meanwhile, we'll want to have position eigenkets which will be labeled with x, y, z. So that represents a state that has definite values of x and y and z, with the projection of psi back on the x, y, z is psi of x comma y comma z. And that piece right there, psi squared dx dy dz interpreted, that represents the probability of finding the particle where?
Within the range of z and dz and x.
Right, so in other words, it's finding it within some little rectangular parallelepiped whose sides are dx, dy, and dz. So it's a probability per unit volume for psi squared instead of a probability per unit length. You're looking pained as you look at that expression. Oh, well, position eigengets, sorry. Eigengets, yeah. Yeah, the eigengets is they gets their own name when they do those. All right, so eigengets, yes, thank you. All right, equals probability of finding particle in volume dx, dy, dz. So you imagine here's your x, y, and z axes, and there's a cute little cube of volume. Right there is a volume element, dx, dy, dz, and so in 3 dimensions, the wave function has units of probability per cubic meter. So it has inverse cubic meters, squared, sorry, it's the square of the wave function has inverse cubic meters as its units. So the wave function itself has meters to the minus 3 halves as its units. Meters to the minus, 3 halves, I guess, right, yeah, this one, yep, right. And there would be similar momentum eigenkets, and if you wanted to transform between them, you'd have to take a 3-dimensional Fourier transform instead of a mere 1-dimensional Fourier transform. What should be something like this? X, y, z, inner product with x prime, y prime, z prime. What should we have that be? Well, if we had this, what did we say that was? What's the inner product of x prime with kx? Yep, delta of x minus x prime. We wanted that to be a Dirac delta function, 0 unless the two are equal to one another, in which case it goes boom and is infinity. So this ought to be, well, we do have such a thing as we call the 3-dimensional Dirac delta function, delta of x minus x prime, y minus y prime, z minus z prime. So in other words, all 3 variables, x, y, and z, have to equal x prime, y prime, and z prime. Otherwise it's 0, but if they're not, it's infinity, and the 4 volume under the curve, so to speak, is equal to 1 in that case. And that is actually just representable as a product of 3 1-dimensional Dirac delta functions. I guess it'd just be the volume. Yeah, let's see, for the area under the, okay, so it'd be some kind of 4-ish volume, whatever. Anyway, the product of the 3 Dirac delta functions in each direction gives you what you want. And if we do something like this, some momentum eigenket represented in the x basis, that's going to be 1 over root 2 pi h bar e to the I p sub x x over h bar. And similarly, in the other two directions, so you get a 1 over root 2 pi h bar for the normalization for each piece, and you get e to the I p x over x, e to the I p x x over h bar, e to the I p y y over h bar, e to the I p z z over h bar. So you get 1 over 2 pi h bar to the 3 halves. And how can I more compactly write e to the I p x x over h bar, e to the I p y y over h bar, e to the I p z z over h bar?
Add them together.
Add them together. And what do I get if I take p sub x times x plus p sub y times y plus p sub z times z? What's that called? What do I get if I take the components of one vector, multiply them by the components of another vector, and add them? That's called the blue, 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 blue of the two vectors.
Projection.
Yeah, but I want a different thing.
Dot
A good old ordinary dot product, yeah. So this is e to the I p dot x over h bar, where the vectors p and x are just the vectors p and x. So in other words, x is x hat plus y hat plus z hat. P is p sub x hat plus p sub y hat plus p sub z hat. So sometimes we'll just say that's the inner product of ket momentum vector that has definite momentum p with ket that has definite position x as vectors. So these are the momentum eigenfunctions. These are the three-dimensional momentum eigenfunctions. This should be the wave function of a particle that has well-defined momentum. This is the wave function in terms of the position basis of a particle that has well-defined momentum, namely p sub x, p sub y, and p sub z. Let's see which one. Stop me when I'm done. Stop me when you're here. Yeah, this to this. Oh, I'm just saying. Let's call that beast. Let's just use that as our symbol for it, and let's call that beast. Let's just use that as our symbol for it. In other words, if it has well-defined values of px, py, and pz, it has a well-defined momentum vector, which we're just calling p, the momentum of the particle. It has a well-defined momentum of some magnitude in some direction. So it's an ordinary arrow. It's an ordinary vector momentum p. No, because these are just eigenvalues. This is a label. So if you want, people don't normally do it, but I could put commas in there just to emphasize these are just labels of the eigenvalues, a list of the eigenvalues. Yes, no, it's not a multiplication. It's just labels of the three eigenvalues. So if you prefer to put commas in there to remind yourself of that, then put commas in there to remind yourself of that. But often people leave those commas out. And then things like the identity look like this. If you're doing it in 3 dimensions, the identity will be an integral over outer products like that. Which again, feel free to put commas in there if you want to remind yourself that that's not x times y times z. That's being written inside there. Those are just labels for the 3 eigenvalues of position that the ket has, that it represents. It's an eigenket of the position operators x, y, and z, with eigenvalues little x, little y, and little z. So you do all the things we did before. If you want to transform from the x basis to the p basis, you would insert the identity in that form and use to get the 3-dimensional Fourier transform. except that you get a plane wave like this with a complex conjugate, because if you do something like, I want to know, what is the momentum space wave function? Well, I can insert the identity, so I'll often write d3x to represent dx, dy, dz, integrating over all space. d3x of p x x psi, and this will be what we would call psi sub momentum vector p star of x, the eigenfunction with eigenvalue p complex conjugate. So that would be then the integral d3x of 1 over 2 pi h bar to the 3 halves e to the minus I p dot x over h bar. And then this is the three-dimensional wave function, psi of x, which stands for psi of x comma y comma z. So this is the three-dimensional version of going from the momentum space wave, from the position space wave function to the momentum space wave function. So we could say psi of p, the momentum space wave function, is the three-dimensional Fourier transform of the position space wave function. The only difference between what we had in this in one dimension is you're doing an integral over volume instead of over one variable. You have to cube that 1 over 2 pi h bar square root that appears out in front because there's one for every direction. And instead of e to the minus I p x over h bar, you've got p dot x instead of just p times x, because we're in 3 dimensions now. So you need the 3-dimensional version of the dot product instead of just the 1-dimensional version of the dot product. Okay, any questions? Alrighty. For a particle described by the classical Hamiltonian, the classical expression for its energy in terms of its momentum and position so the classical Hamiltonian will generally look like H sub classical is p squared over 2m, that's the kinetic energy, but it's the momentum vector squared, which means p dot p, where the vector is its dot product with itself. And here I mean just the ordinary dot product. I'm thinking of an arrow. You're just an ordinary momentum plus some potential energy as a function of x, y, and z, which I'll write v of x arrow for compactness. So that means v of x, y, z. So expanded out, in other words, we're saying it's p sub x squared plus p sub y squared plus p sub z squared over 2m, the kinetic energy, plus the potential energy, which in general will be a function of all 3 position variables. The Schrödinger equation in the coordinate basis, position basis, becomes IH bar d psi dt, so I'm using capital psi. In other words, the wave function is going to be a function of x, y, z, and time. So the capital psi is the one that includes the time dependence. So it's psi as a function of x, y, z, and t is equal to minus h bar squared over 2m. And then instead of just d squared dx squared, like we have in one dimension, or partial with second partial with respect to x, now we've got one for all three coordinates. So there is second partial with respect to x plus second partial with respect to y plus second partial with respect to z. So you get the generalization of p squared over 2m operator to 3 dimensions applied to psi, plus d of x, y, z, psi of x, y, z, t. So this looks just like the one-dimensional version, except that v and psi are position dependent in all three directions now, and there is a momentum operator squared for each of the three coordinate directions. Just like the one-dimensional version, to get the one-dimensional version from this, you just take out all the y's and z's and just leave x, and you're in the one-dimensional version. So this is the natural generalization of the Schrodinger equation in one dimension. But of course, the fact that now we're in 3 dimensions makes things even more entertaining than they were before. Now, does anybody know what that beast right there is often called? The sum of the second partials.
Del squared.
That's good old del squared. That's right. That's del squared, also known as the Laplacian. Yeah, the Laplacian operator. What's that? Yeah, Pierre Simon de Laplace, or however you say the French name. That's my bad French. Pierre Simon de Laplace. Notice that we can make a vector momentum operator, which is formally just the x momentum operator x hat plus the y momentum operator y hat plus the z momentum operator z hat. So I'm using capital letters when I want to emphasize this is an operator here, and small letters when I want to say this is just a variable. So notice I'm hatting the unit vector, so I better not hat the operators because then I'm using hat to mean 2 different things. So I'm using capitalization to mean, hello, I'm an operator. All right? So this is minus IH bar ddx x hat plus ddy y hat plus ddz hat. It's an operator, right? It's lying in wait. An operator is an instruction to do something, right? So it's okay for this just to be sitting there. It's lying in wait for some poor unsuspecting wave function that it can jump on and create d psi dx x hat plus d psi dy y hat plus d psi dz hat. So this is the instruction to take the derivatives in all 3 directions and form a vector whose components are those derivatives in the different directions multiplied by minus IH bar. And if you're okay with this, you should be okay with this, because this is a perfectly well-defined instruction on what to do if a wave function happens along. Differentiate with respect to all 3 coordinates, multiply by unit vectors, and make a vector out of it, in other words, whose components are minus IH bar d psi dx, minus IH bar d psi dy, minus IH bar d psi dz. This operator is often called the what's the, yeah, it's the gradient operator, which gets the symbol, yeah. I just put an arrow on top of the upside down triangle. That's just the gradient operator. Note that, in fact, as an operator, the Laplacian literally is del dot del. If we just imagine taking ddxx hat plus ddyyy hat plus ddzz hat and symbolically dot it with itself, where the product of two operators, remembers, means do one and then do the other. So again, everything is implicitly waiting for a poor innocent function to come along for it to pounce on it. Because when I take this dot product, x hat dot x hat is equal to 1. It's not a vector, it's just the number 1. And y hat is 1, and z hat dot 1 is 1. So this is d squared dx squared plus d squared dy squared plus d squared dz squared. So we can say that the momentum operator maps onto minus I h bar grad in the coordinate basis. In the positional coordinate basis. And the p squared operator maps onto minus h bar squared times the Laplacian. You can take p dot p as an operator. You'll get minus I h bar times minus h bar grad dot grad, which is minus h bar squared del squared. So minus h bar squared Laplacian. So notice that our Schrodinger equation has 1 over 2m times the square of the p operator applied to psi, which is the kinetic energy operator. P squared over 2m is the kinetic energy operator, which is minus h bar squared grad squared over 2m. So our Schrodinger equation says I h bar d psi dt equals kinetic energy operator plus potential energy operator times psi, which is the same thing we had in one dimension. It's just now we've got the three-dimensional version of that. Okay, any questions? Can I erase this stuff? The time-independent Schrodinger equation should be wet then in 3 dimensions. The times. Well, what is it in 1 dimension? The time-independent Schrodinger equation is, I'll start, minus h bar squared over 2m d squared psi dx squared plus b of x psi of x is equal to e psi of x. You get that by separating variables. You do the same thing in 3 dimensions and it generalizes in the natural way. It's right side of the time-independent of the time-dependent Schrodinger equation equals e psi. The same thing is true in 3 dimensions. So you get minus h bar squared over 2m grad squared psi, which stands for, and notice I'm not capitalizing it now because I'm looking for a time-independent stationary state. Stationary state in terms of the spatial piece of it. Grad squared psi, so it's a sum of partials now. It's not the total derivative with respect to x. The the second total derivative, because psi depends on x, y, and z, plus v psi equals e psi, and I could put I could put the dependencies in there, v of x, y, z, psi of x, y, z equals e of x, equals e psi of x, y, z, blah, 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 but I'm just not bothering to do that. It's just a number. So that is our three-dimensional version of the time-independent Schrodinger equation. So we're going to be looking for eigenfunctions of the Hamiltonian, eigenfunctions being called the energies of the states, where, for example, if we're dealing with hydrogen, V will be the Coulomb law potential energy function. That's really what hydrogen wave functions represent, is they're solutions of this equation where V is the Coulomb potential energy between a proton and an electron. And the equation will be written in spherical coordinates because while it looks more complicated in spherical coordinates, it's actually solvable in spherical coordinates. While it looks easy in Cartesian coordinates, it's virtually impossible to solve it in Cartesian coordinates other than by first solving it in spherical coordinates and then substituting for x, y, and z in terms of r, theta, and phi. Sure, you can do it that way, but, good for you. So for hydrogen, we'd be looking at V as a function of just distance from the center. We convert to spherical coordinates. It would be minus e squared over 4 pi epsilon naught r, where r is the distance between the proton and the electron. E minus is the electron, so distance between E minus the electron and the proton. Epsilon naught is the permittivity of free space, and E is the charge on an electron, by which I mean magnitude of the charge. Now, we could write that in terms of x, y, and z. We could write v of x, y, z equals minus e squared over 4 pi epsilon naught. What's r in terms of x, y, and z? Square root of x squared plus y squared plus z squared, right? So I have the hydrogen Hamiltonian. If I just plug in that for V, but the spherical symmetry says, well, basically what it comes down to is ouch. Trying to solve that thing with the square root of the squares, some of the squares in it is ouchy. This is much easier in form. The problem is, as we're about to see, grad squared becomes much more complex. And I don't mean complex as in imaginary real part. I mean just more difficult looking when we write it in terms of spherical coordinates. But nevertheless, the simplification that results from that in V more than makes up for the complication in the Laplacian that results from that. So, we're going to talk generically about spherically symmetric problems. Only later will we specialize to hydrogen, because every spherically symmetric problem has the same angular dependence for the wave functions. The only thing that changes is the radial dependence. The angular dependence is always the same. The angular dependence translates into the angular momentum properties of the wave function. And we're going to see that just like with the harmonic oscillator in one dimension, we could define raising and lowering operators and do everything via the algebra of the raising and lowering operators, or you could use a series solution and deduce Hermite polynomials and all that sort of thing. algebra of the operators was in fact easier in the end, we're going to see that with angular momentum in 3 dimensions, we can define raising and lowering operators and do everything algebraically. We can reduce all the eigenvalues algebraically, and in fact, we're going to see, oh, not all angular momentum is spin angular momentum. You can have eigenvalues. I mean, it's orbital angular momentum. Not all angular momentum is orbital angular momentum. So we'll see from the algebra that you can have half-integer values of angular momentum, and that'll say, oh, there might be some other kind of angular momentum than orbital angular momentum, and in fact, we'll see, oh yeah, there is. It's called spin angular momentum, and we use matrices to represent the spin operators and so forth. So it'll be quite lovely. And we won't have to, at that point, have to know anything about doing Legendre polynomials and so forth in order to associate the Legendre functions and so forth in order to get the eigenvalues for the angular momentum. Of course, all that will mean more to you when we actually do it, so let's launch upon that path, shall we? Problems with spherical symmetry. Curious to know if you guys ever talked. Did you guys ever talk about angular momentum, raising and lowering operators in PChem?
Not really.
You did talk about raising angular momentum, or no?
No.
No. Okay. All right.
I was amazed by that whole ladder operators.
Yeah. So we're going to get ladder operators and angular momentum too. So I don't know if folks do that in PChem or not. So did you ever see those, Charles, when you took PChem or whatever?
No.
Yeah? Okay. All right. This will be fun then. Okay. Good. So see a new perspective on things. So, if the potential energy depends only on distance from the origin, that's what I mean by spherical symmetry. Then spherical polar coordinates are the natural choice. Remind you how those work, and point out that mathematicians and physicists interchange what we call theta and phi, unfortunately. So here's x, y, z. Here's some point, and we want to give it spherical coordinates. R is the distance of the point from the origin. Theta is the polar angle, the angle between the line from the origin to the point and the z-axis. Mathematicians call it phi. What did you guys call it in PChem? Did you guys call that theta? All right, physicists and chemists unite against those mathematicians. And then we project down onto the xy plane, and the angle phi is what we call that azimuthal angle, or what the mathematicians call theta. So for now, at least, if you're taking a math course, that you have to do it. But anyway, phi and theta are as described there, and we're sticking with it. And the conversions from from r theta phi back to x, y, z are x is equal to r sine theta cos phi, and y is equal to r sine theta sine phi, and z is r cos theta.
Why do physicists change the notation?
From what mathematicians do?
Yeah.
I don't know how that started. I mean, in a sense, I kind of have to admit. See, physicists are inconsistent because we call polar coordinates just in the plane r and theta. But if we want to be consistent, we should be calling them r and phi in the xy plane. But unfortunately, physicists say r and theta in the xy plane, and then inconsistently decide that it's phi when you go to polar coordinates, to spherical polar coordinates. Whatever. I actually use r and phi in plane polar coordinates just to be consistent. And then the mathematicians can't have any beef with me. Call the angles anything I like. I call them alpha and beta. I can call them Fred and Sally. You know, it doesn't matter. So those are the transformations. Not hard to figure those out. In other words, if you just drop a perpendicular onto the z-axis, hypotenuse is r, projection along the same, you know, the adjacent side will be r cos theta, so that's where z equals r cos theta comes from. Then meanwhile, if I project down onto the plane, I'm looking at the side opposite angle theta, and so that would be r sine theta for hypotenuse r there. And then, if I project that onto the x and y axes, I'll get r sine theta times cosine phi to get the adjacent side, so that gives me x, and r sine theta times sine phi to get the opposite side, and that tells me y. So that's where those transformations come from. After much entertainment, we find that the Laplacian in spherical coordinates is, so you can do a change of variables. There's actually a more elegant way to do it, but that would take us way far afield. So the interested reader can entertain him or herself as they see fit. It turns out that the Laplacian in spherical coordinates is, instead of just second partials with respect to x, y, and z added up, it's more entertaining. It's 1 over r squared, partial with respect to r, of r squared partial with respect to r, plus 1 over r squared sine theta, partial with respect to theta, of sine theta partial with respect to theta, but wait, there's more, plus 1 over r squared sine squared theta, and at least this piece is easy, second partial with respect to phi. So as promised, the Laplacian becomes a mess in spherical coordinates. But nevertheless, as hard as it might be to believe, it is a tractable mess. In other words, it's not so messy that you can't end up solving, as long as v is behaving itself and is not too weird a function. You know, v is the inverse hyperbolic tangent of r times the sine of r over, you know, I can make up v of r's that are going to be like, okay, have fun with that one. But what we're going to do here is look for separable solutions. In other words, we're going to see if we can find solutions psi of r, theta, and phi that factor into a function of r alone that we call capital R, and a function of theta and phi that we call capital Y. And later on, we're going to find out that those capital Y's are what are called spherical harmonics, and standard notation for spherical harmonics uses capital Y. And so that's, you know, kind of anticipating what has come before. You might at first want to factor into a product of R, and a function of R, function of theta, function of phi. Trust me, this is the way to go.